good. That's going there. Cool. All right. Yeah, I am late. Eating lunch. So I'll keep my camera off for a little bit. All right. Any questions?
Not exactly sure how to get started on factorial problems for homework 6.
Okay. Hold on, I'm reading Corbin's factor theorem. The sum of factors of the number 2 to the n plus 2 to the n minus 1, excluding the number itself, where n is greater than or equal to 2, is always greater than or equal to the number itself. I believe that because the factors of 2 to the n minus 1 will be, the factors of 2 to the n will be 1, 2, 4, 8, all the way up to 2 to the n. And so that'll take you to 2 to the n minus 1. That's an interesting theorem.
I tested it all the way out to 4096 plus 8192.
Cool. Yeah, publish it. So if you write powers of 2 in binary, sometimes that's interesting. And like I say, with 2 to the n, the factors are just powers of 2 up to that number. 2 to the n minus 1, though, is a different story, because sometimes that's actually prime, and sometimes it's not. So adding those factors in, I don't have a good intuition right now for what that might give you. But that sounds like a cool discovery. Hey, I got a camera. Cool. All right, well, let's talk about factorials. And so, as I was telling someone earlier today in office hours, the goal of this latest homework set is really to understand induction, right? But and so that's, knowing the two steps, the base step, the inductive step, and so on. It's knowing how to state a family of propositions, what the inductive step is, and so on and so forth. But then there's also the mechanics of how you actually show. Usually Pn implies Pn plus 1. And for math problems, that usually involve some kind of algebraic manipulation. And for these factorial problems, like that second homework problem, that can be challenging. And I'm looking mainly for, the machinery of the induction, having the right steps and so on, more than I'm looking for, how clever can you be about expressions involving factorials. But some things to keep in mind when you're trying to do things with factorials. So n factorial is just the product of all integers up to and including n, right? Integers bigger than or equal to 1. And so if we look at n plus 1 factorial, it looks like this. Product of all integers up through n plus 1. But since this is n factorial, we can also write n plus 1 factorial as n factorial times n plus 1. And this is probably useful for that first factorial problem on the homework set. So that's one thing to keep in mind. Another thing to keep in mind is sometimes we can find patterns by using specifics. And we can't prove patterns with specifics, but for example, if I just write down 4 factorial equals 1 times 2 times 3 times 4, 3 factorial is 1 times 2 times 3, 5 factorial is this, that might make it easier to jump out at us like, oh, this thing right here, this is just 4 factorial. So 5 factorial is just 5 times 4 factorial. And this thing right here, 4 factorial, well, this piece is just 3 factorial. So 4 factorial is just 4 times 3 factorial. And that might lead us to speculate that n factorial equals n times n minus 1 factorial, which is another version of what we wrote here. So I'm going to say play around with those kinds of things. Look at some specific values for n or I or whatever variable you're using, and see if that leads you to notice some patterns. And then play around with writing these things out and see if you can work your way towards some sort of useful algebraic manipulation.
I find myself struggling with the problems on the second, in the 3.5 section, where it seems like there's potentially 2 different, the first one doesn't have an inequality, but it seems as though you almost have to treat it like it.
So what questions are we looking at there? Do you remember what the question numbers are?
It's 3, so in 3.5 it's 1, I believe it's 1, 8, and 9.
Okay. Let's see.
Yeah, 1, 8, and 9.
So prove that n plus 1 n plus 2 is a multiple of 3 for all integers. Eight is an inequality, 9 is an inequality. The inequalities are different, but I'll start on one. So let's look at number 10. So prove 2n plus 1 is less than 2 to the n. We're playing without a safety net here because I haven't done this one yet. And let's see, we're 12 minutes in. Go ahead and send me an attendance note, please. Oh, good timing. So, Pn is the proposition 2n plus 1 is less than 2 to the n. And we're asked to show that for n bigger than 3. I think it's true for 3 also. So 2 cubed would be 8, 2 times 3 plus 1 would be 7. So it's actually true for n bigger than or equal to 3. So we can show the base case, right? P of 3 says 2 times 3 plus 1 is less than 2 to the third. This is 7. This is 8. That's true. So base case, absolutely true. So assuming that n is bigger than or equal to 3, let's show Pn implies Pn plus 1. So P of n is our hypothesis. 2n plus 1 is less than 2 to the n. That's the definition of Pn. And in my mental scratch sheet over here, my ignore section, I'm trying to show p of n plus 1, which means I'm trying to show 2 times n plus 1 is less than 2 to the n plus 1. So any ideas how we might show this from that?
We can expand it out first.
Let's write this side as 2n plus 1 plus 2. Right, so 2n plus 2 plus 1. So I've got my 2n plus 1 plus 2. So when I move from n to n plus 1, I'm adding 2 to the left side. And over here, I'm doing 2 to the n plus 2 to the n. That's 2 to the n times 2, or 2 to the n plus 1. And if I know that this thing is smaller than that thing, if I can show that 2 is smaller than 2 to the n, this inequality will follow. So I might do something like this. N is bigger than 1. And so 2 to the n is bigger than 2. Because exponents work that way if everything's positive. So n's bigger than 1, we know that because, n is bigger than 3. N is said to be, so yeah, 2 to the n is definitely bigger than 2 because n is bigger than 3. Bigger than or equal to 3. So this is certainly true. And so I'm going to modify this and say 2n plus 1 plus 2 is less than 2 to the n plus 2, because I've got this inequality already. That's p of n, and so I'm just going to add 2 to both sides. And now I'm going to use the fact that 2 is less than 2 to the n and show that this is less than 2 to the n plus 2 to the n. Right? Because I'm adding, something smaller here and something bigger here. And inequalities are transitive, so this tells me that this is smaller than that. Sorry, this is 2 times n plus 1 plus 2 is less than 2 to the n plus 2 to the n. And now you just kind of reverse what you did on your mental scratch paper. So we go ahead and we say that 2 to the n plus 1 plus 2, well, that's 2 times n plus 1 plus 1. And this is 2 to the n plus 1. And then we simply observe this is p of n plus 1. So the particulars for a given problem will be different. But the general idea is write down what you know, inequality, equality, whatever. Think about what you're trying to show, and then just stare, right? I've got this. I want to get this. And inequalities are usually easier than equalities. I mean, they're harder because there's more to choose from, but, if I know this, how can I show that? And chances are with these inequality type questions, the inequality just gets more and more severe as n gets bigger. And so you've usually got a lot of kind of wiggle room to play around with. And it's a puzzle. It's a hunt of some sort, right? It's looking for the a way to take this and turn it into something like that. And again, it's not the main idea of an inductive proof. It's a necessary step. But I'm definitely more interested in what comes before this and what comes after it than knowing that particular connection. Does that help at all?
Not yet.
So yeah, you could say properties of inequalities here. As long as you don't skip too many steps, right? If I tried to go directly from here to here, and I didn't do any of this stuff, I would be like, wait a minute, how did you get from here to here? So you want to show enough steps with enough explanation to make sure that whoever is reading your proof doesn't have to figure out what you figured out. See, if you've got to go through 3 steps and do a transitive thing here, just put that in your proof, right? And the whole idea of the proof is, you know, hey, I have seen the light. I have seen why this is true. I'm going to share it with you. And so your presentation is basically a way to not just, you know, give the person the punchline, but take them through the steps so that they can convince themselves, oh yeah, okay, this follows from that, and this follows from that. Oh yeah, this must follow from that. Okay, I believe it now. And that's kind of the nature of pretty much any proof. That's also the nature of, you know, scientific discovery. Trying to prove that mice breathe air, you know, whatever it is. So let me do one more induction example, and I want to pick on another problem from the homework set. Well, another problem from that part of the book that we're taking our problems from. And so this is not one of the assigned problems, but I want to go through something similar to what we're doing, but I want to do it in a little more detail and just make sure that we're clear why we're doing these steps. So this is going to be a more careful induction proof. And so here's a theorem. Let me just get it out of the book. Alright, so let's do this one. 1 plus a third plus a ninth and so on and so forth equals this funny looking expression. So let's do it like this. 1 plus a third plus 1 over 3 squared plus all the way up to 1 over 3 to the n is equal to 3 halves times 1 minus 1 over 3 to the quantity n plus 1. Alright, so let P of n be the proposition. And I want to do this without the dot dot dot, because I think the dot 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 sometimes hides what's actually going on. And if we write this with summation symbols and indices and so on, that can get, you know, more complicated. But I want to do this at least once, because I think it can also help explain why we're doing the steps that we do. So I'm going to write P of n as the proposition that the sum from I equals 0 to n of 1 over 3 to the I is equal to 3 halves times 1 minus 1 over 3 to the n plus 1. And I'm starting from 0 in this case because our formula here is 1, which is, 1 over 1, which is 1 over 3 to the 0. And then when I equals 1, that's 1 over 3 to the 1, that's this term, and so on and so forth. So P of n is this proposition. And we want to prove P of n for all n bigger than or equal to 0. So we need a base case. That's the case where n equals 0. So P of 0 says the sum from I equals 0 to 0 of 1 over 3 to the I equals 3 halves times 1 minus 1 over 3 to the 0 plus 1. That's just plugging in a 0 for n, right? This is what P of n is. P of 0, just plug a 0 in right there, right there. Alright, well the sum from 0 to 0 of 1 over 3 to the I, this is just, 1 over 1. So P of 0 says that 1 over 1 is equal to 3 halves times 1 minus 1 over 3 to the 1, which is 3 halves times 1 minus 1/3, which is 3 halves times 2/3, which is equal to 1, and 1 over 1 is equal to 1. So this is true. Alright, but when you're doing the base case, right, you've got a proposition P of n, you're plugging in a particular value for n. In this case 0, typically we do a 1, but in this case we're just plugging in a 0, and we're saying P of 0 says this is equal to that. Well, we can simplify this expression as just 1 over 1, we can simplify this expression as 3 halves times 2/3, so P of 0 is saying 1 over 1 equals 3 halves times 2/3. And you keep rephrasing what this proposition is saying until it's saying something that we can all agree is true. P of 0 basically says 1 equals 1. And that's true. And remember, I'm writing equivalent statements. This is equivalent to that. 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 I'm not doing funny things like multiplying both sides by something and saying, hey, after I did that, the two sides are equal. I'm actually saying that this equals this, and this equals this, which equals that, which equals that, which equals that. Alright, so that's the base case. So the inductive step. So let's show P of n implies P of n plus 1. So prove P of n implies P of n plus 1. And this is where n is some number bigger than or equal to 0. Okay, statement 1 will state P of n, that's a hypothesis. Step 2 will say what P of n is, and I'm going to use this, thank you, this more written out explanation of P of n, which is the sum from I equals 0 to n of 1 over 3 to the I is equal to this big mess on the right, 3 halves times 1 minus 1 over 3 to the n plus 1. Alright, I want to show something about P of n plus 1. So let's just write down what P of n plus 1 says. P of n plus 1 says sum from 0 to n plus 1 of 1 over 3 to the I equals 3 halves 1 minus 1 over 3 to the n plus 1 plus 1. Alright, this is what we have to show. If we can show that this is equal to that, we are done. We'll have proven P of n plus 1, and then we can use induction to say, therefore, P of n is always true. That's really good. Well, we know this. right? We're assuming P of n, so we know that this is true, and we're trying to show that this is true. And so here's this point in our inductive proof that we need to find something clever to do. And this is the only thing I know, this and like algebra, right? And this is what I'm trying to show. Well, you know, maybe there's some way to turn this into that. But, you know, it's going to involve increasing the exponent over here, and I'm subtracting from something and I'm multiplying. That feels kind of complicated. But there's a really simple way to change this into that. And the simple way is, summations have this cool property. If you want the sum from I equals 0 to n plus 1 of some function, it's the same as the sum from 0 to n plus the sum from n plus 1 to n plus 1. Right, we can split these sums into pieces. I can go from 0 to a, and from a to b, that's the same as going from 0 to b. And think of it as a for loop in programming. If I make a for loop from 0 to n plus 1, well, I could do a for loop from 0 to n, and then I could do one more iteration for n plus 1. So I'm basically going to write this down. I'm going to say the sum from I equals 0 to n plus 1 of 1 over 3 to the I equals. Now why am I doing this? Because this looks just like the left-hand side of what I'm trying to do. I'm trying to show this is equal to that. So I'm starting off, I'm just writing down this left-hand expression, and I'm trying to use what I already know, statement 2 here, P of n. So I can use this property of summations and say this is equal to the sum from 0 to n of 1 over 3 to the I, plus this kind of silly sum, the sum from n plus 1 to n plus 1 of 1 over 3 to the I. And then I can write this as the sum from I equals 0 to n of 1 over 3 to the I plus, well, how do we do a summation from n plus 1 to n plus 1? Just substitute n plus 1 in for I. This whole thing here is just 1 over 3 to the n plus 1. Well, now I've got the left-hand side that I'm trying to prove is equal to something, and I've got something right here which looks just like what I wrote in step 2. And so I can take this part, and I can use step 2 and say, hey, this is 3 halves, 1 minus 1 over 3 to the n plus 1. And then this is 1 over 3 to the n plus 1. This is n plus 1. I haven't changed anything yet. All I'm doing is algebra. But the way I chose to do my algebra was to try to do something to take what I already know and turn it into part of what I'm trying to show. I'm not doing any substitutions though, right? I'm not just arbitrarily setting n equal to n plus 1. I got this n plus 1 down here because I very deliberately added 1 over 3 to the n plus 1 to both sides of this. When I added it to the left, this just became a summation with a higher index. When I added it to the right, well, I just added it to the right. But now, since this looks like the left side of what I'm trying to do, now all I have to do is show that this is equal to that. And now this is where we get into, you know, playing the games of algebra to see if we can somehow rewrite this. And that's you know, its own subproblem. But this is algebra, right? So this is what you've done in 111 or whatever, and it's trial and error, and it's you know, taking walks and staring at clouds and waiting for inspiration. or whatever. But you know, one good thing to do is multiply things out. It's usually easier, not always, but usually easier to work with something if you don't have all these parentheses and, you know, multiplication and addition and subtraction all jumbled together. So I might write this as, and let me write this a little neater. So 1 minus 1 over 3 to the n plus 1 minus 1 over 3 to the n plus 1. That's just exactly what I had written there without the scribble. And so let's multiply the 3 halves. So 3 halves times 1 is 3 halves. 3 halves times 1 over 3 to the n plus 1 will be 3 halves times 1 over 3 to the n plus 1. And then I'm going to leave the minus 1 over 3 to the n plus 1. And now you might notice something, which is we've got a 1 over 3 to the n plus 1 popping up twice. And so this will be 3 halves minus...
Sign flip?
Oh, it's very possible. Did it? 3 halves minus that.
On your last one.
And this
We
one.
added it up there and now you're subtracting it.
Thank you. Very good. Alright, so yeah, plus 1 over 3 to the n plus 1. That would have cost me the rest of the class. Alright, so we have this common term here, we can factor that out. So let's do 3 halves, and this is going to become a minus 1 times 1 over 3 to the n plus 1. So this is, you know, minus 3 halves times that, minus a negative 1 times that will be the plus 1. I have a bad feeling about this. Alright, spot the algebra error. Here's an exercise. It's 1 3 to the n plus 1. Right, so remember we're trying to turn it into... Where'd my sheet go? We're trying to turn it into this thing. Any thoughts?
You should have factored it out.
But I think there's a math error somewhere, even if that wasn't the right technique.
What are we trying to turn it into again?
We're trying to turn it into this. And so the left side is already set up with that summation up to n plus 1. And so we're trying to turn the right side into this. So let me copy this, ignore. We're trying to get to 3 halves times 1 minus 1 over 3 to the n plus 2. So let's just proceed confidently. So this is 3 halves minus, and 3 halves minus 2 halves is 1 half times 1 over 3 to the n plus 1. How do we turn this into that? We've got, ignore the 3 halves. How do we turn 1 half times this into this thing?
I don't think we can take a half out of both of those terms, can we?
So I did 3 halves minus 2 halves gives me a half. We could take a half out of both of those. So here's the magic. Let's throw some magic dust around here. 1 over 3 to the n plus 1. We can also write this as 3 over 3 to the n plus 2. In other words, we can multiply this by 3 over 3. So we increase the power of 3 on top by 1, we increase the power of 3 by 1 on the bottom. And once you've got it in this form, then it just kind of falls out. And then you factor out the 3 halves. Right, and that's the form we're trying to get to. So there's all this work that happens before you get to this point where you need this insight, right? And to finish the proof, you still need this, right? But you've still got to do all of this work beforehand. And if you see this insight and you write down something like this and this, that really doesn't get you any points, right? It's really about, stating what you're trying to prove, expressing a family of propositions, stating a base case, showing the base case is true, and then stating the inductive hypothesis, and then doing a formal proof of that, starting with P of n, writing out what that means, and then doing something to get you, close to or all the way to P of n plus 1. Yeah, well, I did this one before class, and I was still oblivious to it for 10 minutes. So, that's not just you. But unless you do algebra every day, we're not good at these kinds of things. But my suggestion is, don't spend 3 hours working on one of these problems, right? Work really hard on the induction setup, right? But when you get to this point of, how do I turn this into that? Spend, 10-15 minutes on it. Change modalities, do, homework from another course or something, come back to it later, come back to it the next day, come to office hours, right? But don't spend, hours beating your head against the wall on something like this, because it's not an algebra course, it's not a factorial course, right? And it's not a homework set on those things, it's a homework set on mathematical induction. And I'd rather you spend those cycles trying to understand this process, but trying to be as clear as possible. Why am I adding this thing to the left side? What allows me to do that? Why is that legal, and why is simply substituting n plus 1 in here not legal? Those kinds of things, right? So try to understand the structure of the proof rather than the particular details of n plus 1 factorial is n times n plus 1 or something like that. And this is the same theme that we left off with on Friday when we talked about pigeonhole principle, and that I alluded to with these problems that very clever people come up with solutions for, and we're not necessarily trying to be that clever. We're trying to understand the underlying principle. And the problems we're working on are supposed to be illustrations of these principles. All right, so I intended that to clarify things. I've got a feeling maybe it didn't, but maybe it will later on. So let's continue with counting. So we talked about the pigeonhole principle, right? Which is where you have n objects and n minus 1 boxes. And if you try to put objects into boxes, you're going to have at least one box with at least 2 things inside it. So that's the pigeonhole principle. There's a generalized version of that. And the generalized principle is when you have n objects and k boxes. And sorry, say again?
What? Hey, you're unmuted.
I got it. All right. So if you have n objects and you have k boxes into which you're going to start placing these objects. And again, you know, you could place them all in one box. You could try to distribute them among the boxes. So the generalized pigeonhole principle says that in this case, at least one box will end up containing at least, and it's a new function perhaps to you called the ceiling n over k objects. And the ceiling operator, ceiling x, is the smallest integer bigger than or equal to x. So it's sort of the opposite of rounding down, but we're not rounding, we're kind of going up to the next biggest integer. Unless we have an integer to start. So, for example, the ceiling of 2 is 2. The ceiling of 2.001 is 3. Smallest integer bigger than or equal to this number. Well, 2 is an integer, so the smallest integer bigger than or equal to 2 is 2. But something just slightly bigger, the smallest integer is all the way up to 3. Ceiling of 2.5 will be 3. Ceiling of 2.99999 will still be 3. That's the smallest integer bigger than or equal to that number. And the ceiling of 3 will be 3. But if we go just a little bit beyond 3, the ceiling is 4. So that's the ceiling operator. And the generalized pigeonhole principle says that if you have n objects and you put them into k boxes, at least one box contains at least the ceiling of n over k objects. Alright, so for example, let's say you're given 25 people. What's the smallest number of people born on the same day of the week? The largest number would be 25. They might all have been born on Tuesday. What's the smallest number of people born on the same day of the week? Well, that's not exactly how I want to phrase it, actually. Yeah, it's 4, but this is not a good way to phrase it because yeah, I guess that works. All right, so let's make 7 boxes. So we have 7 boxes, so k equals 7. We have 25 objects, that's the people, n equals 25. And now we're putting people into boxes based on what day of the week they were born. Generalized pigeonhole principle tells us at least one box contains at least ceiling 25/7. What 25/7 would be 3.571428, and the ceiling of that is 4. So at least one box contains at least 4 people in it, which means there's at least one day of the week that's shared by 4 people or more. So that's the generalized pigeonhole principle. And it comes in useful sometimes working problems in reverse. So, so suppose you have 52 cards, and you have 4 suits. So clubs, diamonds, hearts, spades. So 4 types of cards. So how many cards?
On your last example there, it was at least 3 people share the same birthday, right?
It's actually 4.
Oh, rounded up, gotcha.
Yeah, so since it's slightly bigger than 3, well, bigger than 3, it rounds up. Ceiling is 4. Alright, so you have 52 playing cards. They come in clubs, diamonds, hearts, and spades. Those are called suits. So how many cards must you draw to guarantee 3 of the same suit? So, you know, you pick one card, it's a club. You pick a second card, it's a diamond. You pick a third, it's a spades. You pick a fourth, it's a heart. Pick a fifth one, maybe it's another heart. Now you got 2 hearts. So I can draw 5 cards and not necessarily have 3 of the same suit. Or, you know, I could pick 5 cards, they could all be clubs. And now I'd have 5 of the same suit. So the question here is, if I'm drawing cards, what's the minimum number I have to draw to guarantee that I have at least 3 cards of the same suit? And this is kind of a reverse direction to how we've been using the pigeonhole principle. And so we're going to picture, you know, 4 boxes. Clubs, diamonds, hearts, and spades. And each card you draw is going to go into one of these boxes based on what the suit is. And you want to know how many cards you have to draw until you're guaranteed at least one box has at least 3. Generalized pigeonhole principle says n objects, k boxes. At least one box contains at least ceiling n over k objects. So we can reword this problem as follows. Find the smallest n such that the ceiling of n over k is 4 in this case is equal to 3.
Wouldn't we use the floor instead, though?
You always use the ceiling for
smallest?
the generalized pigeonhole.
Okay.
But the answer that we end up with, that will be the smallest value. Certainly if you know, picking 15 cards guarantees that we have 3 of the same suit, then certainly picking 16 or 17 or 100 cards will also guarantee that. But the smallest number would say, you know, 16 would guarantee it, 15 does not. So something like that. So we can change this into a purely mathematical question, which is find the smallest integer n such that the ceiling of n over 4 is equal to 3. And so this is a chance to sort of experiment with this function and think about ceilings. So if we remember this, right, the first time we get to a ceiling of 3 is when this thing we're taking the ceiling of is bigger than 2. So if n is equal to 8, ceiling of 8/4, that would be 2. But if n is equal to 9, ceiling of 9 for us would be the ceiling of 2.25. That would go up to 3. And so this is the critical point, and so n equals 9. And now we can think about that answer and see that it makes sense, because if you pick 8 cards, you could have 2 of these, 2 of those, 2 of those, 2 of those. You don't have 3 of the same suit. But as soon as you pick a 9th card, it's going to go into one of these bins. Whichever bin it goes into, that one you've got 3 of that suit, and that's what we're after. So in this case, the answer is 9. Well, we get it by sort of taking this and changing it into a statement of the conclusion of the pigeonhole principle, in this case, that we want this to be true. Right, right. All right, so just like with some of these other problems we looked at last week, there's a cool little theorem we can show with this principle. So here's a clever little problem. Given n plus 1 positive integers, less than or equal to 2n, one always divides one other. Yeah, that's horrible English. Yeah, so back on this one, how many cards must you draw to guarantee 3 of the same suit? So yeah, it's possible you draw 9 and they all come out with clubs, right? So you drew 9 cards and they all came out. And it's possible, you know, if you want 3 of the same suit, maybe you only draw 3 cards and bingo, you've got 3 of the same suit. But that's not guaranteed. You could draw 3 cards and get, you know, 1, 1, 1. Or maybe 2 here and then 1 here. And you could draw 9 cards and end up with 9 diamonds. But the question is, to guarantee that you've got at least 3 of the same suit, what's the minimum number of cards you have to draw? And that's what the answer will be, 8. So yeah, slightly different question.
Can you go back to that last one real quick?
Mm-hmm.
What was the minimum number of cards?
Minimum number of cards will be 9.
So how is it 9? I mean, as I think about it logically, like if there's, you know, 13 cards per suit,
Mm-hmm.
and I want 3 cards of the same suit,
Mm-hmm.
to guarantee, don't I have to draw at least, you know, 13 times 3 plus 3 to guarantee that I get 3 cards of any single suit? Because, I mean, if they weren't randomized at all, and I stacked, you know, clubs, diamonds, spades, or something like that, I mean, I guess it's not inclusive of any one suit.
So,
inclusive of one suit.
right, so if you needed to guarantee that you got 3 hearts, yeah, you'd have to do 39 plus another 3. But we're just looking for 3 of the same suit. It's not specified which suit that is. So if you stack the deck and you had all clubs in the beginning, you draw your first 3 cards, you're done, you got 3 clubs. But I think you're addressing if you wanted a particular suit, right? Like you want diamonds, those could all be at the very bottom of the deck. In your first 39 cards, you wouldn't even have a single diamond yet. But that's a different question. So this is just looking for 3 that are the same as each other, without regard to whether that's clubs or diamonds or something else.
So I put 2, 2, 2. The 9th card has to be 1 third card of one of the 4.
Exactly. All right, so this is a horribly worded statement, but let's pick a number like n equals 10. So the challenge here is, can you find 11 numbers between 1 and 20 such that none of the numbers you pick is a factor of another number? So we're picking numbers between 1 and 20. Well, we can't pick the number 1 because that's a factor of everything, but we could pick the number 2. And we could pick 3 because 2 is not a factor of 3, 3 is not a factor of 2. We can't pick 4. We could pick 5. We can't pick 6 because these are both factors. We could pick 7. Can't pick 8. Can't pick 9. Can't pick 10. We could pick 11. We can't do 12. We could do 13. Looks like we're mainly doing prime numbers, right? 14, 7's a factor. 15, 16, 17 is okay. 18, 2 is a factor. 19, so how do we do? We found 1, 2, 3, 4, 5, 6, 7, 8 numbers. And the goal is to find, in this case, 11 numbers. And you know, if we pick 2 as one of our numbers, we lose all of the even numbers. So we're only going to have n numbers left to choose from. So we could instead, you know, start off with 3 and 4 and 5. And we can do 7. We can't do 8. We can't do 9. We can't do 10. We can do 11. We can't do 12. We can do 13. We can't do 14, 15, 16. We can do 17. We can do 19. 3, 4, 5, 6, 7, 8. So we found 8 numbers there, right? But not 11. So this theorem is that if you pick some number n, some integer n, and you pick any n plus 1 positive integers up to and including 2n, at least one of them is a factor of another one. And this can be shown using the pigeonhole principle. So I'm not going to go through the proof of this today. I'll leave you to think about that. I will not ask you something this subtle on a test. But if you're interested in thinking more about pigeonhole principle and how it can be applied, play around with this. It's a fun problem. And I'll give you a hint. If you have any number, we can write it as 2 to some power times an odd number. In other words, any number we can factor out a bunch of powers of 2 from and write it as some power of 2 times an odd number. And it's very easy to count the odd numbers between 1 and 2 to the n and use that for a pigeonhole principle. Alright, so I'll leave that for your contemplation. But I want to move on. I want to talk about permutations. But let's do a 5-minute break, and send me an attendance note. And let's do a break. Let's come back at 4.5 minutes from now. So 13:38. All right, so let's move on. Let's talk about permutations. So this is another application of counting. And as with some of these other things we've discussed, this will start off maybe fairly obvious, but it'll get more interesting. I guarantee. So let's start with a definition. A permutation this is an ordered arrangement of objects. And the ordered part is going to be critical. After this, we'll talk about what are called combinations. Combinations are unordered. But a permutation is an ordered arrangement of objects. So a completely different story from, say, when we did set theory, where we had sets which were an unordered collection of objects. Permutation is an ordered collection. And so, for example, I have 3 pens. I have a green pen, I have a long black pen, and I have a silver pen. And here's a particular arrangement of these 3 objects. This would be called a permutation of these 3 pens. This is a different permutation. This is a different permutation. This is also a different permutation. So is this. So is this. It turns out with 3 pens, there's 6 different ways I can arrange these. So the number of permutations of these 3 objects is 6. All right, and there's a related definition, which is what we call an R permutation. So an R permutation is an ordered arrangement of R objects. So again, suppose I have 3 pens. This would be an example of a 2 permutation. It's an ordered arrangement of 2 pens. This is also a 2 permutation. So is this, so is this, and so on. Alright, so you got the idea? Permutation, just an ordered arrangement. And an R permutation is an ordered arrangement of R objects. And these pop up in studying problems related to, well, how to arrange things. So for example, let's say you have 5 students. And we want to choose 3. Let me say pick. Choose is a particular word. Let's pick 3 to stand in a line for a picture. So we got 5 students. We're going to make a picture containing 3 of them. They're going to be standing side by side. And we could say, how many ways can we do that? How many different ways could we pick 3 students out of 5 and arrange them, side by side? So if our students are named A, B, C, D, E, well, we could pick students A, B, and C and line them up like that. We could pick students A, B, and C and line them up like that. We could line them up like this. We could do lots of things. Or we could, pick students A, B, and D and line them like that. Or do D, B, A, or dab, or bad, or, whatever. And there's a lot of ways that we can pick 3 students out of 5 and place them in a particular order. Do we know how to figure out what the answer to this is? How many ways we can pick 3 students out of 5? If I offered you $1 million,
Isn't it like a factorial something?
it's something. But we learned a rule last week. All right, so someone said 5 times 4 times 3. That's correct, but why is that the formula? Why does that give us the answer?
Because there's 3 positions, and the first position has n, and the second position has n minus 1, and the third position has n minus 2.
All right, so what's the rule that's at work here? Somebody make my day. The blank rule.
I missed last week, so
Oh,
thanks for Friday.
okay.
Product rule?
The product rule, thank you. This is the good old product rule. We can take this task of putting 3 students in a line and break it down into a set of 3 subtasks. First task, we pick the student to stand in this first position. And we have 5 ways we can do that. And then we pick a second student to stand in the second position. We only have 4 ways to do that because we've only got 4 students left. And then the third task is to pick someone to stand on the right. And we only have 3 students left, so there's 3 ways to do that. So there's the number of ways we can complete our task. So this is really just the good old product rule. But we're going to make it look fancier than that. So we're going to define a new symbol. This is a function, p, parentheses, n comma r. It's a function with 2 variables going in. And this is the number of r permutations of n objects. And in general, so we did it for the case of 5 objects where we're picking 3. So we've shown that p5 comma 3 equals 5 times 4 times 3. But we can do exactly the same line of reasoning for n objects where we're picking r of them, which is the first object that we're going to pick. Well, we have n choices, so there's n ways to pick the first object. And then we have to pick the second object, and there's only n minus 1 ways to do that. And then we have to pick the third object, and so on, all the way down to the rth object, where there's going to be n minus r minus 1 ways to do that. And this is unpleasant to work with, especially the n minus r minus 1 business and so on. But if we do the math and we think about factorials, right, these numbers are getting smaller and smaller. We're going from n minus 1, n minus 2, all the way down to 1. And if we divide by this extra stuff over here, n minus r, n minus r plus 1, 1, right? I've taken this thing and I've multiplied it by 1. Remember, we mentioned sometimes it's useful to multiply things by 1 or add 0 to something if you come up with a clever way of writing 1 or 0. So here we're writing 1 as just this over this. But when we do this, and this may not jump out at you right now, but this is n factorial, right? It's the product of all integers from 1 up to n, and this is n minus r factorial. So if that doesn't click, don't worry about it. You can take this as just kind of a given. Number of r permutations of n objects is equal to n factorial over n minus r factorial. And that's going to be something you can put on your note sheet and you can use in solving problems related to permutations.
What exactly is R?
The number of objects that you're picking. So 5 students, and you're trying to pick 3 out of 5.
Oh, okay. So it's like a filter, kind of.
Yeah. All right, so we can go to town with this formula. So let me keep this up here, and let's just start using this and see some examples. So suppose you have a running race and you have 10 runners, and you're going to have 3 medals. You're going to have gold, silver, and bronze. First, second, and third place, right? And how many possible outcomes are there? In other words, how many ways can somebody awarded first place, second place, and third place be? And so this is a permutation question, right? We're trying to pick 3 runners out of 10 and place them in a particular order: first place, second place, third place. So yeah, this is P10, 3. And so if we use this formula, that's going to be 10 factorial over 7 factorial. And that works out nicely because 10 factorial looks like that, and 7 factorial looks like this. And so guess what? All of this stuff cancels. And you're just left with 10 times 9 times 8, which looks a lot like our product rule. But this factorial form sometimes makes it easier to work with. So 9 times 8, 72 times 10, 720 possible ways that medals could be awarded. Three medals, or 3 places. All right, 6 people. Seated at a table with 6 chairs. All right, so you've got a group of 6 people. You're trying to choose 6 of them and place them in a particular order, right? If we just number our chairs from 1 through 6, or A through F, we can say how many ways can we rearrange these 6 people. Well, this is just P6, 6. 6 people taken from a group of 6. And our formula tells us this is 6 factorial over 6 minus 6 factorial. Anybody know what 0 factorial is?
Is that just 0?
0 and 1.
It's actually 1, which makes no sense. But that's what it is.
One way to take from the empty bag, and that's nothing.
Yeah. So 6 people, and you're trying to arrange them. That's a 6 factorial, and this is why factorials pop up a bunch in these questions. So 720 ways to arrange 6 people.
So 0 is just basically, the 0 factorial is just n to the 0 power. Right, so it's just 1 no matter what.
So this is a useful diversion to end on, because we've got to end in about 4 minutes. But 0 factorial, I mean, it makes no sense, right? N factorial is what you get when you multiply all the integers from 1 up to n. But 0 factorial would mean multiplying all the integers from 1 up to 0, and you can't get to 0 starting at 1, right? So it's kind of a silly thing to think about. But nonetheless, we talk about it. And so how many people here have finished their calculus sequence? I don't actually need a show of hands. But if you finished your calculus sequence, then you may have encountered something called the gamma function. And the gamma function is this bizarre little function like this. And for positive integers, it looks like factorials, but it's also defined for fractions, and it's also defined for negative numbers. And so gamma n is actually n minus 1 factorial. So gamma 4 would be 3 factorial, that's up here at 6. Gamma 3 would be 2 factorial, which is 2. Gamma 2 is 1 factorial, which is 1. And gamma 1 turns out to be 0 factorial, which is also 1. And so the gamma function is how we can expand the notion of factorials because it agrees with factorials on integers. But it's also got values for non-integer values, and it's got values for negative numbers except for negative integers. And the gamma function is really this infinite integral. Gamma z is x to the z minus 1 e to the minus x integrated with respect to x. And it's defined for imaginary numbers too, as long as the real part is bigger than 0. And so this is tied into this idea of analytic continuation. If you have a function that's defined over some small set of things, sometimes you can find a nice function defined over a bigger set that matches up on that smaller set. And if it satisfies certain properties, we can call that the analytic continuation, and we can talk about uniqueness of that function. And so from this gamma function, we can conclude that 0 factorial is equal to 1. But also cool things because it has some interesting values like at 1/2. So yeah, no, let's not do that one. But 1/2, I think it's the square root of pi. Yeah. So minus 1/2 factorial is the square root of pi, which is kind of cool because, you know, multiplying integers shouldn't get you to pi, but it does. So that's a fun function to play with. All right, send me an attendance ping on the way out. Let me read a question from someone, but you're good to go. Have a good one. I will see you tomorrow. And let me read a direct message I got and reply offline. Yeah, so when I said no additional switches when compiling, I didn't mean you can't use -O. But don't use things that change, you know, the version of C or something like that. But yeah, GCC -O is perfectly fine. That's a good thing to do. So you're good.
You can still just submit a single C file, right?
Yeah, you can just upload a .c file to Canvas. And I'm basically going to download all of those on Wednesday, push them over to the Linux server, compile them, run them, and then grade them from there.
Okay.
All right, cool, awesome.
Can I ask you a quick question?
Sure.
It's very fast. On PA4 for 224,
Mm-hmm.
I'm working on the delete command. I was able to get